Alright, so in this tutorial we're going to continue on with our discussion of the components of a circuit, and then we're going to define the key measurements that go along with the circuit and put it together ultimately to look at how energy is delivered, or more specifically the rate at which energy is delivered. Before we get to that, I have 6 schematics of circuits, and we want to apply the rules which we loosely talked about in class to see if we get energy delivered in a manner that is prescribed for a circuit. Okay, so let me remind you of what you have a circuit. You have 3 components. You have a voltage source, you have wires leading from the voltage source and coming back, and you have to pass through a load. Not only do you have to have them, they have to complete a circuit. And what that means is you have to have a path or multiple paths that pass from the positive to the negative terminal of the battery and pass through a load in the process. So if any one of those is not met, you will not have energy delivered. And so that's what we want to look at in these 6 examples before we get into the discussions of measurements. So let's take a look at the first circuit. So we have a battery where this is the positive side and the negative side, and we have 1, 2 loads. So what we have to ask yourself, is there a load or loads between the positive and negative connected? And if we follow this path, we can get from positive to negative and pass through the loads. So this is definitely a go. Okay, now we're going to learn this later on, but since we have 2 loads and there's only one path, this is the definition of a series circuit. You don't have to worry about that right now, but we're going to come back to that when we have multiple loads. All right, I think I also asked you to put the direction of the current flow. All right, so the current flow would be from positive to negative, as is the convention. All right, circuit B. We have a battery, the positive, negative. We have a load, but then we have another battery. Okay, so there is a complete circuit. Would this work? So think to yourself, and then I'll answer in a minute. All right, hopefully you answered no, this would not work. Why not? It's basically because we have the positive connected to a positive. All right, and if you will, between them, the negative connected to a negative. And when you have a negative connected to a negative, or a positive positive, there is no potential difference across the circuit. While this might have a positive 6 potential difference, this would have a negative 6 because of the way they're connected. So they're opposing each other, nothing happens. All right, C. Take a look at that. We have a switch here. Okay, so is there a connection from the battery to a load in a complete circuit? And the answer is yes. This would work. It would go clockwise. What's going to happen in the bottom part of the circuit? Absolutely nothing. Even though there's no load there, the fact that there is a break there where the switch is means that none of the charges are going to move in that part of the circuit. So this is essentially a simple circuit with the potential to make it more complex by closing the switch. All right, D. We have battery, we have wires, we have loads. Are there paths to get from positive to negative? Here's the positive, here's the negative, and yep, I've got a path right here, and I also have another path that takes me from positive to negative. So both of these loads will work, they'll heat up or they'll light up, but since there's 2 paths, they are connected very differently than A, and this is what we call a parallel circuit. Okay, we'll talk much more about those later on. All right, looking at E. E's a subtle one. All right, so you have a path through here, but you also have another path this way where there's no load. Because there's no load here, we call this a short, for short circuit. And when there's a short circuit, only the charges that are in that short will move. Nothing will move in here. So this is a no, even though there is a path through the resistor. That short kind of shortcuts everything, and that's usually a dangerous thing in a circuit because none of the energy is going to go in the load. It's all going to be in the wires, and that's usually not desirable. All right, the last one. We have a loop through this one, and we have a loop through this one. Okay, so that's fine. The difference is we have a parallel branch, once again, kind of like D, and within that parallel branch, we have a series connection. So this is the most complicated of the circuits that we have to understand, is when we have a combination of series parallel, but we'll tackle that another time. All right, so let's move on to the things that we can measure about a circuit. So I'm coming back to the components that we discussed earlier in our lesson. Now we're going to look at things we'd measure about them. So let's jump right into it. So our voltage source, what we'd measure about it is voltage. A lot of times we measure differences in voltage, potential drops. Okay, so I'm going to put that in parentheses. But voltage is the key term, and its symbol is capital V. Okay, that makes sense. So there's an equation that I'm just going to throw at you. I'm not going to explain to where it comes from, that defines voltage. All right, so voltage is defined as energy or work, but we'll call it energy, per unit charge. Okay, so if I have a 6-volt battery, what that's basically saying is for every coulomb of charge, Q, that moves in the circuit, I will deliver 6 joules of energy. All right, it's just a way of quantifying how much potential there is before we move anything through it. I'm not going to say much more about that, except that based on its definition, the units would be joules per coulomb. And that has a name. You can probably guess. It's a volt, which oddly enough has the same unit as our variable itself. So if I might say V equals 6 volts, V equals 6 V. So that's the one measurement where the unit and the variable have the same symbol. Don't ask why, but you want to understand the joule per coulomb part. Alrighty. The wires and conductors, all right, so what are they there for? Well, they provide charge and the charges move through them. So one of the key things we want to measure about that charge movement is their flow. So we call the charge flow current, electrical current, and its symbol is capital I. Not sure why. C is already taken for, well, it's not really taken for anything. Current is widely misunderstood at what it means. Its definition, in terms of an equation, is the rate at which charge moves through a circuit, Q over T. This is not to be confused with the speed at which the charges move. That's always a distance divided by time. Q over T basically is like mass flow rate. Think of when we were doing water moving and we had mass moving. It's how much mass passes by a certain spot in a river. We'd have a lot of mass moving by for a wide river versus a narrow river, irrespective of how fast you're moving. So in a circuit, if we were to zoom in on one part of the circuit, we were to measure the amount of charge that moves by in a unit of time, that is electric current. Okay, so the charges could be moving really, really slowly, which they actually are, but if you have a whole lot of them moving by a given spot, then you have a large electric current. And so on this definition, we see that Q over T, it's going to be units of coulombs per second. And a coulomb per second has a special name called an ampere, or an amp for short, and that's given a symbol, letter A. Okay, so let's talk about that a little bit more conceptually. So current is by definition the flow rate of charge. In other words, if mass flow rate was m dot, current would be q dot, or just q over t. All right, and all the necessary charges are there. That's a sea of mobile electrons. All right, why do we care about current? Because current is, if it's a moving of charges, why do we want charge moving? Because they're delivering something, they're carrying something, they're carrying energy. And so if you've got more current, you're going to deliver energy at a greater rate to the load. So more current leads to more power output or energy output. Okay, so that should be pretty straightforward. If I think of charges like little trucks carrying energy from one place to another, the more trucks that I have moving by, the more power I can deliver. The question is, how do you get more current? Well, we'll address that at another time. Our body, especially our skin and muscles, are very sensitive to current because our muscles and the nerves work through electrical currents. So if you're wondering how big is an ampere of current, well, ampere of current, if we are flowing through something, is 1 coulomb per second. So that should kind of give you an idea that that's pretty large because a coulomb is a huge amount of charge. So if we were to have as little as 1,000th of an amp flowing through us, that can be painful. You would not like that feeling. Okay? If you up it to 15 thousandths, then you lose muscle control. All right, so that happened to me last year where I grabbed a hold of 2 wires and I had a few hundredths or a few thousandths of a current, amperes of current flowing. I could not let go of them until I fell back. And that's very, very, very painful. If you only go up to 7 hundredths of an amp, that's enough to stop your heart. And that's what the danger is with electrical circuits, at least in the home. The ones we'll be doing with the class, they're not going to be dangerous. And if you get 5 to 10 amps, well, that's going to fry your muscles. Okay, now you're bypassing all your nerves and all that. You're just going to cook your muscles, and that's really what electric chair does. So if you want to deliver a lot of energy, you want a lot of amperage. Okay, that's what hurts. That's what kills. Voltage doesn't kill or hurt. It is amperage does, but usually high voltage leads to high current. And that's actually what I'll talk about here. The amount of current depends on 2 factors. Okay, the primary thing is the voltage across the circuit. And another one is the resistance of the load. And we'll discuss that later on next week. Okay, so just understand you can't just dial in a current and whatever current you want. It's a response to how you set up the circuit. And one thing you control, 2 things you control in a circuit are what you put in the circuit and the voltage. All right, so the last measurement that we want to look at is power. Okay, the rate at which energy is developed in the circuit, usually in the load. Right, the whole point of setting up a voltage source and having current flow is to deliver energy. So the load resistor, one of the things we can measure, this is another thing, but we'll come back to later, is power. Of course, that's P. We already know that P is by definition energy per unit time, the rate at which we're converting energy. And of course, the unit is a joule per second, which we already know is a watt. So what we want to do is we want to be able to relate voltage and current to power, because if you want power delivered, you need current flowing and you need an energy input. So there should be a pretty simple connection between the two. Okay, in fact, we can use in units. So I'm going to come back here. So more power requires more voltage and or more current. All right, so how can we get power from these? Well, let's look at the units. The units of power are joules per second. We know that voltage has units of joules per coulomb, and we know that current has units of coulombs per second. So I don't think it takes too much to figure out that if I have some combination of these 2 measurements that give me joules per second, what would I have to do mathematically? Well, if I multiply them, I see that the coulombs cancel out, leaving with joules per second. So what that tells us then, whoops, I'm going to come back here. I guess that's the definition. Let me add another thing here. So power, power by definition is energy per unit time, and then in an electrical circuit, it's most easily calculated as a product of voltage times current. Okay, so we'll be using that quite a bit. So we have 3 new equations: voltage, current, and power. They should be in your reference tables, so you don't have to memorize them. So in the 2 minutes I have left, let's start a problem here. So I got a toaster. There's my load. It's plugged into a standard US outlet. That's important. It draws 10.5 coulombs per second of current. So that's I for a time of 120 seconds. That's T. So what is the voltage across the circuit? Well, we can't calculate it, but the fact that it's a standard US outlet tells us that it's 120 volts. So that's just something worth knowing. All right, now I can ask how much charge flowed through the circuit at this time. So like any problem in physics, if you're not sure what to do, just let's identify what we're looking for. So I'm looking for charge. That's Q. What do I know? I know voltage, I know current, I know time. Well, there must be an equation as Q in it, of course. There's a few of them, but the one that's most straightforward is I equals Q over T. So Q is going to equal I times T. If I plug in the numbers, I see that I get a very large number, 1,260 coulombs. That's a lot of charge that moved through the toaster in 2 minutes. You might say, well, wait, that's 1,200 lightning bolts worth of charge. Isn't that really dangerous? The answer is no, because remember, there's basically limitless charges in the circuits. It's all neutral. It's not like a buildup of that. So you're not going to get shocked by 1,200 joules or lightning bolts worth of charge. All right, how much energy was delivered or transferred to the voltage source? Okay, so the one equation we have there's a few of them. The most direct one is that we know that voltage by definition is energy per unit charge. So we could say that the energy delivered is the amount of charge moved multiplied by the voltage which it goes across. So we take the 2 numbers that we already have and we get 151,000 roughly joules. So that's a lot of energy. But a joule is a small amount of energy, so don't be deceived by that. Okay, and the power of that P is simply V times I. Okay, you can work that out. So try the rest of these before this is up.